All right, today we're diving into a classic problem from Irodov, a book that's been, a rite of passage for physics students for decades. But we're not just here to find an answer. Nope, we're here to learn a powerful method, a framework that you can use to solve some of the most challenging problems in mechanics.
So here's the puzzle. Just picture it. You're designing the ultimate ski jump. You've got this total height, h, to work with, and you get to decide how high to make the launch ramp, little h. Now here's the catch, right? If you make that ramp too high, the skier won't build up enough speed. But if you make it too low, they're not in the air long enough. Our job is to find that perfect balance, that absolute sweet spot to get the maximum possible distance.
Okay, here's our game plan. We'll set up the challenge and grab our physics tools. Then, we'll figure out how the disk gets its speed and what happens once it's flying through the air. And finally, we'll hunt for that sweet spot and reveal the winning combination. Simple as that. Let's jump in.
Now, before we write a single equation, let's do what any good physicist does first. We break the problem down. You have to see this not as one big complicated motion, but as a story with different parts. And each part, well, it follows its own physical laws. Our first job is just to pick the right tool for each part of the story.
So we're going to split this problem into a two-act play. Act 1 is the slide. This is where our disk is sliding down, trading height for speed. The perfect tool for that? The law of conservation of energy. Then comes Act 2, the flight. The moment the disk leaves the ramp, it becomes a projectile. And for that, we'll switch gears and use the principles of projectile motion. Two parts, two different tools.
Let's look at our first tool. The problem gives us a huge clue when it says the hill is smooth. That's code for ignore friction. And if we can ignore friction, it means mechanical energy is conserved. So all the potential energy the disk loses as it drops from h down to h gets converted one for one into kinetic energy, into pure speed. That's the key to figuring out how fast it's going right at launch.
Okay, time to put this into practice. We're going to set up a little energy balance sheet. The rule is simple. Whatever total energy we had at the very top of the hill has to equal the total energy at the very instant the disk leaves the ramp.
And here's what that looks like. On the left side, at the top, it's all potential energy, mgh. The disk is just sitting there. On the right side, at the launch point, that initial energy has now been split into two things. There's still some potential energy left, mgh, but the rest is turned into kinetic energy, 1/2 mv squared. Now for the really satisfying part. Notice how m, the mass, is in every single term. That means we can just cancel it right out. Poof, gone. And that's a huge insight, right? It means the launch speed doesn't depend on how heavy the disk is. So after a little rearranging, we get this beautifully simple expression for the launch speed, squared. It only depends on gravity, g, and how far the disk has actually fallen, which is h minus h. This little equation is the bridge to the second half of our problem. So now our disk is in the air, it's a projectile. And here's a super common pitfall you have to avoid. Don't try to describe that whole curved path with one monster equation. The trick, and I mean always, is to split the motion into two separate problems, what's happening horizontally and what's happening vertically.
This is where the magic really happens. Think of it as two separate worlds. In the horizontal world, once the disk is launched, nothing is pushing or pulling it, so its speed v is constant. The distance it travels, s, is just that speed times time. Easy. In the vertical world, gravity is the only thing that matters. It's constantly pulling the disk down, and the time it takes to fall that height, h, is all that determines how long it's in the air. Now here's the key. The time is the one thing that connects these two worlds. We find the time from the vertical equation and then plug it into the horizontal one to get our distance.
So, let's bring our two worlds back together. We take that launch speed we found from the energy part and we combine it with the flight time we just figured out. And when we plug them into our distance formula, all the other stuff like gravity just disappears. It's amazing. We're left with this incredibly clean and elegant equation. The final distance, s, depends only on the total height, h, and our choice for the launch height, h. This is exactly what we need.
And this brings us right to the heart of it all. We've got the formula that tells us how far the disk will fly for any launch height we pick. But we don't want just any distance. We want the biggest one possible. We want to maximize s. So the question is, what value of h makes that happen?
Let's look inside this equation. To make s as big as possible, we need to make the stuff inside the square root as big as possible. And what's in there? It's a product of two things, h minus h and h. Now think about what those represent. H minus h,
That's related to our launch speed, and h is related to our flight time. We're trying to maximize the product of a speed term and a time term. This is that trade-off we talked about at the very beginning, but now we see it in the math. And this chart shows that trade-off perfectly. If you make your launch height h really high, then h minus h gets tiny and you have almost no launch speed. The disk just kind of flops off the edge. If you make h super low, you get a ton of speed, but you have no flight time. It just hits the ground instantly. The maximum, that sweet spot, is right there in the middle, where you've got a good balance of both.
Now, you could absolutely use calculus here to find the maximum, but there's a much more elegant way to see it. Think about this. If I give you a fixed length of fence and tell you to make a rectangle with the biggest possible area, what shape do you make? A square, right? The product of the sides is biggest when the sides are equal. It's the exact same idea here. We have two numbers, h minus h and h. What's their sum? It's always just h, a constant. So to make their product as big as possible, those two numbers have to be equal.
So using that beautiful principle, we just set our two terms equal to each other. The speed part, h minus h, has to be equal to the time part, h. And just look at that. It's a super simple equation. A tiny bit of algebra from here, and we've got our answer.
So we did it. We broke down the problem, we applied the right physics, and we found the point of perfect balance. Let's put it all together and see the final answer.
And there it is. The perfect launch height, the one that makes the disk fly farther than any other, is exactly h divided by 2. You use the first half of the drop to build up speed and the second half to get your flight time. It's just so perfectly symmetrical.
But wait, it gets even cooler. What is that maximum distance? Well, if you plug our perfect height, h over 2, back into our distance equation, the math just works out beautifully. And the result is kind of mind-blowing. The maximum possible horizontal distance is exactly equal to the total initial height, h. How elegant is that? You know, getting the answer h over 2 is great. But the real prize here, the real takeaway from this explainer, is the method we used. This 4-step process. Break it down, pick your tools, link the parts, and then find the optimum. That's a powerful toolkit you can use for tons of other problems, not just in physics, but anywhere you're looking for the best possible outcome.
And that's our deep dive into this problem. But before we finish, I'll leave you with one last question to chew on. What if the hill wasn't smooth? What if there was friction? How would that change the answer? Would you want that launch ramp to be higher or lower than h over 2? Think about it. Thanks so much for watching.